Let's now look at kernel density estimation. So with kernel density estimation, we are looking at a softer estimation than what we have with the naive histogram. So instead of having this kind of W function that is relatively crisp, that is between plus and minus h around x, we have 1, and out of that we have 0. We are looking as to use a softening kernel. Typically, we are using a Gaussian kernel. This is not the only kernel, but we will use, for example, a Gaussian kernel, which is basically to put some kind of function that is similar to a Gaussian distribution as the way to evaluate the effect of the samples around the point at which we are looking at. So this function is that one here. So 1 over square root of 2 pi. So this is kind of one part of the Gaussian distribution. And inside the exponential, we are minus u squared divided by 2. So what we are doing here is that we are making a convolution of the softening kernel over the data set that we have at n. And so this convolution gives us the density estimation, an estimation of the density, for example, at x. So here, the estimation of the density at x is equivalent to convolve, and so the convolution here is basically to make a summation. We are summing the value of k, so we are kind of putting a Gaussian kernel on every sample that we have, and from that we are estimating the value at x, and this corresponds to that. So the kernel is determining the shape of influence over the data. So using a Gaussian kernel is basically to say what is close as big influence, what is far away as much less influence, and it is decreasing as an exponential. So it's kind of decreasing relatively quickly. When we are going far away from x, it is symmetric. It is centered on the value x here that we care in our kernel density estimation. But this kernel can be more or less wide, and this is parameterized by the h value here that allow us to get us a kernel that is maybe flatter and wider, or sharper and with a bigger peak center on the x value. So yeah, so the with h is determining the influence of the data, and this model is generalizing the naive estimation, because naive estimation is that the same thing with the difference that we are using a rectangular box as kernel compared to a Gaussian kernel here, for example. So here are some results with the same data set again with n samples. We see that with a bandwidth of 10, everything is kind of smooth, so we don't see much. Probably it is certainly too wide. Likewise, with a small bandwidth of 1, we have many peaks. This is also not a good thing. So we have peaks here, peaks here, and kind of bump here. So I don't think it's the right estimation. The interesting ones are with bandwidth of 5 or bandwidth of 2, where we see an estimation that is relatively coherent with the real data distribution here. But without these bumps here are relatively here. We see them, but they are not that big, not that kind of visible and there. And likewise, here we don't have any bump, but the peaks here are relatively not that high, not as high as we would like to get, like here and there, which are much better. And even I would say here and there, they are really good, but this estimation is sensitive to these samples. So the width of the window greatly influences the estimate. So with a small h, each data has an important local effect, while with a large h, we have a much smoother estimation, a lot of overlaps between the kernels, but possibly not that accurate. I mean, we are losing a lot of precision locally. We can demonstrate that when the number of samples goes toward infinity, our estimate will tend toward the real distribution. So this is possible, but we have to get a window, an H value that tends to 0. But this should be slower. It's kind of subtle, you know, we want to go toward infinity. So we want to have a really huge data set or infinite size data set, for example, which is of course not computable, but we want to get n close to infinity and we want to get H close to 0. But in fact, the ratio of n times H should go toward infinity in the sense that we should have a data set that is increasing faster than the width of the window that is than the reduction of the width of the window. Typically, we set the H to be equivalent to some kind of H1, which is the base values, divided by the square root of n. This is a rule of thumb. This is not the only way to do that, but that's something that makes sense as a way to adjust the size of the windows according to the dataset size. So if we are looking at the effect here on the 3 columns, we have different bandwidth. So bandwidth of 2, of 1, and 0.5. So we go with a slightly larger to a slightly smaller window size versus on each row is in fact with n equal 10, 100, 1000 samples. So we see that by increasing the number of samples, we've got different estimates. So we can see here that with a really small bandwidth, with few samples, that case here, this is kind of noisy with a lot of peaks. This is not appropriate. The result here is not interesting with that value. But with n equal to 1000 samples, we can see that we have a kind of good estimate, slightly with kind of a lot of variations locally. So these are like, let's see, this has some kind of noise given that we don't have 10,000 or 1 million of samples. With 1,000 of samples, we still get some variation, but still, if we are looking at how close is the estimation from the real distribution, it is pretty close. But we have also similar results here with less variation, so it is smoother, and I would say that the estimation is not as good as the one with bandwidth of 0.5, but it is relatively good. And here with bandwidth of 2, everything is kind of much smoother, but still usable. When we decrease the number of samples with 100 samples, I would say here this is not good. Here this is too smooth. The nice trade-off is in the middle. So with bandwidth of 1, with 100 samples, we've got something that is kind of reliable, while with say 10 samples, a bigger bandwidth makes much more sense. The question here is now to say what kind of soft-turning kernels can we use? So we have some desirable properties, things that we want. We want to use kernel that has these properties. First, we want to get a kernel that is always positive or at least has 0 values. We don't get one, we are not necessarily able to manage kernels with negative values. So over all the domain, the value should be positive or 0. Second property, we want the area under the curve. So we need to be able to integrate the kernel from -infinity to +infinity, and this should be equal to 1. So like, for example, if we have this kind of square kernel that we have with naive estimator, so center at x, x minus h, x plus h, and we should remember that the 8 was equivalent to h divided by 2, if I remember well. So the area under the curve is equivalent to 1 because it's basically h divided by 2 times 2h. Likewise, with the Gaussian kernel, it's kind of similar. The the whole thing should integrate to one. It also needs to be centered on the origin. So basically, when we are integrating, so the average about the expectation. So when we are integrate the x times kx from minus infinity to plus infinity, that should be equal to 0. That allows us to have a kernel that is centered on 0. Why? Because if we have something, so this is what we have. We see it is centered on x, but basically when we are looking at the function here with the box of the naive kernel estimator, it is centered at 0 in its formulation, but when we are using it, we are kind of moving that box over x. So basically here, when we are making this integration, it will integrate at 0. Likewise, for the Gaussian kernel, it is also centered at 0. Why doing this? Because it allows us to have an unbiased kernel. Otherwise, if it is skewed in some ways, the estimation will also be skewed toward, according to the shape of the kernel. We can see that if the two first properties are followed, are respected, the kernel will allow us to obtain a valid density function estimation. And the estimation will be usable as any kind of density function. So it is a density function based on data, but still usable as a density function as any other. The third one allows us to have something that is better in terms of estimation. So one interesting thing is that if our kernel function here, multi-softening kernel, is continuous and differentiable, our estimation based on that kernel is also continuous and differentiable. So this is really nice because we can make even developments, or we can compute the derivatives of p hat with this. This is the case with the Gaussian kernel. So with the softening kernel as the Gaussian one that we just saw before, we have a function that is continuous and differentiable. While the box, it is not continuous and differentiable. One thing that we are looking also is what we call the support. And so the support is define the spread of the values around which it is non-zero. So the support for the squared kernel is basically, when we see it's minus h plus h, the support is 2h. And then the question is, what is the support for the Gaussian kernel? The support of the Gaussian kernel is infinity because it is never really 0. So there's always a value, even though far from the 0 value, when we are going away from the origin, the support is the value is really small, can be super small, but still it is non-zero. So we consider the support here is kind of important, is infinite. So we have different possible softening kernels usable. We know the Gaussian one, so it is differentiable, but the support is not bounded. We have what we call the boxcar top hat squared kernel. So this is basically the naive histogram kernel that we saw before. So the support is bounded here, but the function is not differentiable because we have this big discontinuities at plus or minus h. So this limits us in some ways. We have other kernels like the Epanechnikov. So this is defined by these functions. This is I would say something that has a shape similar to Gaussian, although it is not exactly that, but it is kind of similar. But contrary to the Gaussian kernel, we have a bounded support. So after at some distance, or with less than -1 or plus than 1, the values is 0. So we have a bounded support, and in between -1 and +1, we have a shape that is similar to the Gaussian distribution. And as such, the estimation is interesting now. So, and it is usable, but it is non-differentiable, non-derivable, because we have a discontinuity at -1 and +1. And if we are looking at the other approaches like the linear triangle kernel, so basically it is something that looks like this. So at -1 plus 1, the value is 0. In between -1 and 0, we are going up and then going down between 0 and 1. Otherwise, we have a 0 value. So here again, the support is bounded, but the function is not derivable. But it is, I would say, smoother than the box R, the square, the naive histogram estimation. It's going up and going down around the origin. We also have the cosinus one, which has abundant support, but not derivable function. So these are different kernels that can be used. I would say at to some point is it important to use one or the other kernel? In practice, it is, I would say, the Gaussian and the boxcar. I would say even the triangle linear ones are useful. The Ibanechnikov can be used. Cosinus is kind of rare, maybe in some cases, but that choice is not. We don't have to define some kind of custom kernel. It is not something that we usually. So in multiple dimensions, we are able to estimate the kernel that way. So it is the same function as before, but generalized for multiple dimensions. We see here that the h is at the power of d. So because this is the size of, I would say, this is a way to normalize everything according to the dimensionality and the size here of our bandwidth, the value of our bandwidth. So it corresponds to what we saw before in d dimensions. So again, we are constrained to integrate the kernel to one. So here, basically, we say we are integrating over the complete domain in d dimensions, and that should integrate to one to allow us our kernel to be usable. Specifically for multivariate Gaussian kernel, which is a multi-dimensional extension of our Gaussian kernel than before. The formulation is this one. So no big surprises here. Of course, we are sensitive to dimensionality. So in many dimensions, this is not super effective. The normalization of values in different dimensions is also important. We want the values in the X vector to be at similar scales, because we have, for example, the Euclidean distance here, L2 norm, in fact, to be precise here. So that L2 norm here assumes that every dimensions are comparable, because if we have like one dimension that is in the scale of 10 power 3, another one is at the scale of 10 power -4, which are completely different. The larger scale, 10 power 3, will dominate completely the other one, and so the Euclidean distance will be based only on that dimension, for example. So it's important to have values that are comparable, normalized. And we can even define a kernel that will include some kind of covariance estimation sigma here. So this covariance estimation is included that way. We are using the inverse of that covariance matrix here. So this is really close to what we saw last week on multivariate multivariate methods using multivariate Gaussian distribution as model. And so if we are using this as a kernel estimation of for classification, so this is possible to use this model for doing classification. So the same thing than before, with the difference that we are looking at the density for class Ci here. So as such, the difference is that we are using the samples from that class Ni, and we are making a sum over all samples, but we are multiplying by RIT. RIT is basically the indicator to use or not, whether or not the sample xt is coming from class I. And this is usable directly to estimate the likelihood of the x coming from that class. And then using, I would say, an estimation of the prior in that way, which is not new. We have a function hi that is a classifier, as we know, but that is based on a kernel estimation of the distribution for that class from these samples at a given point x. And so if we are expanding this, the formula looks like that. Okay. The difference here is, if you ask what is the difference, we have ni here and n here. Why? Because we are multiplying by the estimation p hat, and that allows us to eliminate ni, but including n here, because it was basically equivalent to 1 over ni hd times ni over n, and so we are simplifying these elements directly in that thing, that to there. So if we are looking at the width of the kernel here, the impact on classification can be seen according to the bandwidth. So this is our true PDF, always repeated at the 3 places. And these are the estimation. So we can see that changing the kernel here has some impact. I would say that the histogram here is rough here, but it's also rough there. So it doesn't seem to have a big impact. So histogram is relatively poor for estimating anything outside 1 dimensions data. While the KDE with the Gaussian, for example, the Gaussian kernel, we see here it is rough as it is with the histogram, because the kernel with the kernel is kind of narrow. With the large kernel, it is super smooth, possibly too smooth. We can see that it is not as sharp as what we have as true PDF. And in between, the estimation is relatively good compared to the true PDF. I would say I like this one. Now, if we compare the Gaussian kernel with Ivanishnikov, we can see that the difference is not that significant for medium, narrow, or large width of kernel.